Hello everyone. What I'd like to do in this video is talk about specifically the graphical properties of inverse functions, and also take a look at some possibly problematic functions when trying to find an inverse. Okay, so I'm going to kind of lead with an example. So, for example, let's say we have the function g of x, and let's say it's equal to the square root of x minus 8. Okay, I think this would be a good time to pause the video, and what I want you to do is I want you to find the domain and range of g of x. It might help for you to graph this function, think about it as the square root function shifted to the right 8 units. Take a second and find the domain and range of this function here. Okay, let's do it. Well, we could think about this graphically if we want to do the domain or the range, and we could also figure out the domain algebraically. So if I'm looking at the graph of this function, well, this is the square root function that's set to shifted to the right by 8 units. So here's 8, and here is the square root function, shifted to the right 8 units. Okay, so we can think about what the domain is. Well, we can see the domain is, anything 8 and bigger. 8 and bigger. So the domain of f is going to be all x, the domain of g is all x such that x is greater than or equal to 8. We can see it from the picture. Now you could have also done this algebraically because we can't take the square roots of a negative. You could have thought x minus 8 has to be positive. Add 8 to both sides. Kabam! X has to be greater than or equal to 8. Algebraically, graphically. Okay. And the range of g is going to be equal to, it's going to be all g of x, or if you want, you can maybe say all y, such that what? Y is greater than or equal to 0. You could have also put all g of x, such that g of x is greater than or equal to 0. So either one would work. I'll go ahead and leave it like this though. Okay? So here is the domain and range. Okay. The next thing I want you to do is pause the video, and I want you to find a formula for g inverse. Take a second to do this. Okay, let's do it. So what we have here is we have that, I'm going to kind of work over here, then I'll write the answer over here. So let's flip out a function notation. So y is equal to the square root of x minus 8. How do we undo a square root? We can square. So what we'll get out is that y squared is equal to x minus 8. From here, we can add 8 to both sides. I guess maybe what I should have done is, since we're doing the inverse, I should have flip-flopped the x's and y's. So let's flip-flop the x's and y's. So here's x and here's y. So this would be x. And this would be y. I guess you could flip it before or you could flip them after. Either way would work. Okay. We'll add 8 to both sides. So we'll get that y is going to be equal to x squared plus 8. And this is the inverse. So we found out that G inverse, right here. We'll see right here. G inverse of x is equal to x squared plus 8. The next thing I want you to do is I want you to find the domain and range of G inverse. A hint, there's really not too much work to do. Okay, all we have to do, we don't even have to look at G inverse. What we should remember is, what is an inverse function? An inverse function is a backwards mapping. The regular function maps me from the domain to the range, but what the inverse function does is it maps me from the range to the domain. So the range of G is the domain of G inverse. And the domain of G is the range for G inverse. So really what happens is the domain and ranges switch, so I just gotta flip-flop these. There's nothing more to it. The domain of G inverse, well, that's gonna be the range of G. So that'll be all x, such that x is greater than or equal to 0. And we'll have that the domain, and we'll also have the range. We'll have that the range of G inverse. That's going to be equal to, well, it's going to be equal to all y, such that y is greater than or equal to 8. So the domain and range flip-flop. That's the key observation of how the inverse functions or the backwards functions work. Okay. This is the next thing I want you to do. So part D, I'll erase this here in a second, but what I want you to do in part D is I want you to graph G of x and G inverse of x. I want you to graph these both on the same axes. Go ahead and give that a shot. Okay, let's go ahead and graph G and G inverse on the same axes. Try to organize all our information here and color code it. So we can actually graph both of these functions just really thinking about simple transformations of our toolkit functions. Okay, so if we want to graph the square root of x minus 8, that's the square root function shifted to the right 8 units. So what we just mark in 8 right here, and that's going to look something like this. Similarly, if I want to graph x squared plus 8, this is where a common mistake would be here. You might say, oh, well that's a parabola, a happy face parabola shifted up 8 units. Okay, but we got to be a little bit careful. Because this isn't just a regular x squared plus 8 function, it's the inverse of a specific function. It's the inverse of G here. Since G has a certain domain and range, G inverse has the opposite, the domain and range flip-flops. I got to pay attention to the domain of G inverse. Really, we're only graphing x squared plus 8. What's its domain? It's only x greater than or equal to 0. So I don't want to graph this whole picture. I only need to graph the right-hand piece. So notice here, the domain is all x greater than or equal to 0, and the range is all y greater than or equal to 8. Here's the graph of G and the graph of G inverse. Do you notice anything interesting? Do you notice anything interesting about these two graphs? Do you notice any symmetric patterns? Maybe try turning your head sideways like this. Notice that if I were to tilt my head sideways, these are reflections of one another. These are reflections of one another if I have a tilted head. Notice here, this is the line y equals x. Notice that these are reflections of one another. These are reflections of one another over this line y equals x. If you folded this paper, these would match up perfectly. This is something that will always happen with a function and its inverse. A function and its inverse will graphically always be reflections over the line y equals x. Let's write that down. It's super important. Any function, not just this function, any function, any function, f and f inverse, I could put g and g inverse, these are just could be any function, name it what you want. F and f inverse, graphically, are reflections about the line y equals x. This will always be true. Now let's think about why. Why will this always be true? It comes down to the fundamental idea that what is true about an inverse function, it's the backwards mapping. What it is the domain and range are flipping. The domain is on the x-axis. The range is on the y-axis. So what are we doing? What are we doing when we flip-flop our x's and y's? We're essentially flip-flopping the axes. So the y-axis becomes the x-axis. The x-axis becomes the y-axis. The domain and range are flipping. So the graphs are going to be reflections over the line y equals x. How beautiful is this? So that's a great thing to remember here. We always have to be paying attention to this. Whenever we have a function and we're finding its inverse, we need to pay attention to what was the original domain and range of the function. Then when I have to find its inverse, I have to think about these domain and ranges flip-flopping. And if I ever have to think about graphically what an inverse function is, graphically a function and its inverse are reflections over the line y equals x. This is so important to know. Let's talk about some problematic functions. Let's talk about some problematic functions. Okay. So we want to keep in our mind that whenever we have a function, we can know what its inverse function looks like graphically by reflecting it over the line y equals x. This now leads us to problematic functions. Some problematic functions. Let's go ahead and take a look at an example. Let's see if I can get a little bit better of a black marker. A little bit better? Okay. So, a great example of a problematic function is f of x. That's equal to x squared. Okay. Let's go ahead and take a look at this. Okay. X squared. Hope you believe that looks like our classic. That looks like our classic happy face parabola. Let's draw it here. Just a little bit different. Well, just a little bit different, just a little bit better. Just a little bit better. Okay. Now what we want to do here is I want to think about what would the graph of the inverse function look like. Now, we don't even have to find it algebraically, we can just think about it graphically. So if I'm thinking about reflecting this graph here over this line y equals x, let's think about what picture we're going to get. Okay. So what's going to happen, let's see how we reflect it. This piece here, this piece is going to stay. I mean, this is the output, since this is the line y equals x, whatever the input is here, it has the same output. When I flip those, this piece will stay rooted. So if I'm reflecting this, you specifically maybe think about reflecting this piece here first. You would end up getting, for its inverse, if it's inverse, let's do it in red. That's what you would get for this first piece, but then I want to continue the parabola. So hopefully you're kind of trying to imagine taking these axes and rotating them. If you took this parabola and rotated about the line y equals x, you'd get this red parabola. What is wrong with this picture? Take a second to think about it. Take a second to think about it. Why is my math brain freaking out? Why is my math brain freaking out about this inverse function? It's because it's not a function. Not a function. Not a function. It's not a function. It doesn't pass the vertical line test. It doesn't pass the vertical line test. One input gives me two outputs. Oh no! This is not a function. This is a problem. This is a problem. This is basically saying that not all functions have inverses that are functions. Now, why is this true? Think about this. Think about why is this not true? Why does x squared not have an inverse? Or why is its inverse not a function? Well, think about it here for a second. There's confusion. There's confusion. For example, if I have x squared and I'm asking you, what x value gets me to 4, so I don't know, let's put 4 here, saying, well, what x value gets me to 4? I'm basically doing the inverse. You have an output of 4, what was the input that got me there? Well, there's confusion. There's confusion. Well, did you square 2 to get me to 4? Or did you square -2 to get me to 4? So there's confusion here. There's confusion. So when I evaluate my red function at 4, what x value gives me an output of 4, you try to plug in 4 and it would tell you 2 and -2. There's confusion. There's confusion. I didn't really draw these inputs and outputs to scale, but there would be confusion. Actually, 2 would be more over here. 2 and -2. Four would be more up here. There's confusion. If I plug in 4, was it 2 that got me there, or was it -2 that got me there? So if you tried to plug in 4 into the inverse, it's going to say, wait a minute, I don't know whether to tell you 2, or I don't know whether to tell you -2. This is a problem. Now, the problem is that x squared is not a one-to-one function. X squared is not a one-to-one function. And I'll talk about how to fix this here in just a second. The problem is x squared is not what we call one-to-one. Problem. X squared is not 1-to-1. What a one-to-one function means, kind of loosely, what a one-to-one function means is that, for every output, let's say a function is 1-to-1, if for every output there is one and only one output. One and only one input to get me there. There is one and only one input to get me there. So, for example, what would be a good one-to-one function? Okay, what's a great one-to-one function? Okay, x cubed is a great one-to-one function. Why? Because for every output, pick an output here. Now here's an output. Okay, what input got me there? Okay, well notice there was only one possible input to get me to that output. This function is one-to-one. Pick any sort of output, pick an output here. There is only one input that could have got me to that output. So this function x cubed is 1-to-1. Another one-to-one function would be, I don't know, how about 1 over x? 1 over x, I hope you believe, looks like this. Notice that this function is 1-to-1 because any output that you pick, there's only one possible input that could have got me to that output. This function is 1-to-1. Okay, what was so special? Let's show you functions that aren't 1-to-1. Can you think of some functions that aren't 1-to-1? X squared is not 1-to-1. X squared is not 1-to-1 because if you pick an output, there are 2 inputs to get me to that output. What's another function that's not 1-to-1? What's another function that's not 1-to-1? So I should write a list here. 1, 2, 1. Not 1, 2, 1. What's a good one-to-one function? We saw x cubed is a 1-to-1 function. Every output, there's only one input to get me there. Another good one we saw was 1 over x. 1 over x looks like this. Okay, what's a function that's not 1-to-1? X squared. X squared, there's a problem with this one. For a certain output, there are more than one inputs to get me there. This is not 1-to-1. Okay? What's another good one? What about 1 over x squared is another function that's not 1-to-1. 1 over x squared, remember, kind of looks like that volcano. This function is also not one-to-one because for an output, there are two inputs to get me to that same output. How about another one? How about the absolute value function? That looks like the classic V. That looks like the classic V. You notice for a certain output, there are two inputs to get me there. So how can I tell whether a function is one-to-one or not? What was I pretty much doing the entire here to realize this? I was using a horizontal line. So notice over here, if I have this output, there's only one input to get me there. If I have an output, there's only one input to get me there. If I have an output, there's only one input to get me there. If I have an output, there's only one input to get me there. How can I tell whether a function is one-to-one or not graphically? A one-to-one function will pass what's called the horizontal line test. The horizontal line test. If the graph only hits a horizontal line one time, for any horizontal line, that means there's only one input to get me to that output. So a one-to-one function passes the horizontal line test. A function that's not one-to-one will not pass the horizontal line test. That means that if I take any horizontal line, that the graph would hit it more than one time. Over here, this function doesn't pass the horizontal line test because the graph is hitting this horizontal line twice, which means there are two inputs to get me to that same output. So if a function passes the horizontal line test, it's one-to-one. Now, this is a great thing for me to understand when a function has an inverse that's a function or not. It turns out that only one-to-one functions will have functions that are inverses. And let's think why. What does it mean to be a function? One input, one output. So a function must pass the vertical line test. That means for every single input, the graph can only cross the axis once. These are all functions. For any vertical line, the graph only hits it once, which means for every input, there's only one output. Function means one input, one output. So if a function doesn't pass the horizontal line test, okay, well, how do I think about a function? It's inverse. It's a reflection over the line y equals x. So if a function is not one-to-one, means it doesn't pass the horizontal line test, that means its inverse won't pass the vertical line test. If you don't pass the horizontal line test, you're not one-to-one, which means your inverse will not be a function. It won't pass the vertical line test. So I should make that a note. So problem, x squared is not one-to-one. I want to make another quick note here. Kind of just a little note. A one-to-one function passes the horizontal line test. Okay. If a function is one-to-one, then its inverse will be a function. Again, because, well, if the function passes the horizontal line test, then its inverse will pass the vertical line test. If a function is one-to-one, then its inverse will be a function. Okay, so one-to-one functions have inverses that are functions. We like one-to-one functions. Okay, let's go ahead and talk about how we usually fix functions that aren't one-to-one. Remember, since this function is not one-to-one, it doesn't pass the horizontal line test, which means its inverse won't pass the vertical line test. Okay, to fix this problem, what we want to do is we want to take a function, especially for x squared, and we want to make a vertical cut, so I get two pieces and each of them are one-to-one. A great place to cut a parabola would be at its vertex. So what I'm going to do is I'm going to make a domain restriction. So let's only actually consider this function. Let's consider f of x, but I only want to think about f of x on the domain all x, such that x is greater than or equal to 0. So, if I'm only thinking about x squared for x greater than or equal to 0, I only have half my picture. And now, with half this picture, this is now a one-to-one function. And now I can go ahead and try to find its inverse. So to do that, we'll write y is equal to x squared. For this exercise, I'm actually, to find its inverse, I'm not going to flip-flop the x and y's quite yet. I'll actually do that at the end. Let's go ahead and solve for x by taking the square root of both sides. So we'd have x would be equal to the square root of y. Now normally you would pick a plus or minus here. But what do I choose, the plus or the minus? Well, notice my domain restriction is x is greater than or equal to 0. So x has to be a positive value, so I need to choose the positive version. Okay, from here I can now flip-flop the x's and y's. So I can say here that, that the square root of x is equal to y. Or what we would have here, I'm going to write it right here, is we'd have that the inverse of this function would be the square root of x. Would be the square root of x. And we could draw that. How about we draw that we'll draw that in pink. So now I would just have the square root function. So if I have x squared, and I'm just restricting this domain to x being greater than 0, then its inverse would be the square root function. Okay, but let's say I make a different cut. Let's say I'm still thinking about f of x, which is equal to x squared. But let's make a domain restriction. We can also restrict it for x less than or equal to 0. For all x such that x is less than or equal to 0. So now I'm only thinking about this piece of the function. We can go ahead and find a formula for its inverse. Okay, so let's say y is equal to x squared. If we go ahead and square root both sides, we'd have the plus or minus square root of y would be equal to x. But in this case, do I choose the plus or minus? Well, x here is a negative number, so I'm going to choose the negative version. Okay, from here I'll flip-flop the x's and y's, so I'll get the negative square root of x is equal to y, or we'll have that the inverse function for this domain restriction is equal to the negative square root of x. So the inverse for non-one-to-one functions depends on how you want to chop up the domain. Okay, let's go ahead and do another example. Okay, let's give this problem here a shot. What I want you to do is I want you to sketch this function. I then want you to make a domain restriction so you have two pieces, each piece being a one-to-one function, and then I want you to find the inverse for each one of those. Give it a shot. Okay, let's do it. Let's first graph this function. So this is a parabola. It's shifted to the left 2 units, so -2 and up 1 unit. So this is where its vertex will be. And let's see, what's its y-intercept? If we plug in 0, we'll get 2 squared, we'll get 4 plus 1, we'll get 5. So here's 5. So the graph is going to look like this. Let's go ahead and make a cut on this parabola down the vertex. So now the right-hand piece will be a one-to-one function and the left-hand piece will be a one-to-one function. Okay. So for our first domain restriction, let's do the restriction. So the domain of f, let's restrict it to be all x such that x is greater than or equal to -2. And let's see what its inverse would look like. So I guess we're going to draw it. Here's -2 and here's 1. Here's 5. We're only thinking about the right-hand piece of it. Okay, now if I were to find its inverse, let's see here, I would have that y would be equal to x plus 2 squared plus 1. You could flip-flop the x and y's now. I'm actually going to choose to do it at the end. So I'm going to solve for x. So we'll get y minus 1 is equal to x plus 2 squared. Okay, then you would square root both sides, so we get the square root of y minus 1 would be equal to x plus 2. You remember we have to introduce the plus or minus. Now we have to decide whether we're choosing the plus or minus. Well, notice, since x is greater than or equal to 2, x plus 2 will have to be positive. So x plus 2 has to be positive. I need to choose the positive version. We could finish solving for x by subtracting 2 from both sides, so we get that x will be equal to the square root of y minus 1 minus 2. So now we could flip-flop the x's and y's, or I hope you can see that the inverse function is going to be the square root of x minus 1 minus 2. Let's go ahead and sketch this. So what is this? This is this is the square root function. It's shifted to the right 1 unit. It's shifted to the right 1 unit and down 2 units. Negative 2. So we're right here. Okay. And notice what happens if we plugged in 5. If we plugged in 5, 5 minus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. So when we plugged in 5, the output should be 0. So here we have the graph of its inverse. Well, it's not a perfect drawing, but notice that these are reflections of one another over the line y equals x. So if we take this function, we make this domain restriction, this will be its inverse. Similarly, if we wanted to make a different domain restriction, let's say we'll do it in red. Let's say I want to make the domain restriction the domain of f. Let's say it's all x such that x is less than or equal to negative 2. Okay? In this case here, let's see what would be true if I want to find a formula for its inverse. Well, I guess let's draw it. I only want the piece that's less than negative 2. So I don't need the green right now. So let's go over negative 2. Okay, let's go up 1. So we'd only care about the left-hand piece here. Okay, so if I were to find the formula for the inverse, we'd have y would be equal to x plus 2 squared plus 1. Okay, I'm just going to go ahead and solve for x, so we'll get y minus 1 is equal to x plus 2 quantity squared. Now we'll square root both sides. We'll have the plus or minus y minus 1 will be equal to x plus 2. But do we choose the positive or negative version? Well, since x is less than or equal to negative 2, x plus 2 will be negative, so I need to choose the negative version. So now we could subtract 2 from both sides, so we get that x is going to be equal to the negative square root of y minus 1 minus 2, or its inverse. Now I flip-flop the x's and y's, and switching back to inverse function notation, this will be the negative square root of x minus 1 minus 2. So now this is the square root function, except the only difference, it's pretty much the same as this one, but the only difference is it's reflected over the x-axis. So we're still going to be shifted down 2 units, so here's negative 2, and we're going to be shifting to the right 1 unit. Will be right here, and it's not going to do this because it's reflected over the x-axis. It's going to look like this. Now notice that these are reflections over the line y equals x. So if we have this function and we make this domain restriction, then this here will be its inverse. And that's how we fix problematic functions. We break the function that's not one-to-one into a bunch of one-to-one pieces, and we find inverses for each of those pieces. Hope you found this video helpful. We'll see you in the next one. Take care.